So today's lesson is going to be on equilibrium. Up to this point in our class, we have been making the assumption that reactions go to completion, meaning the reactants get completely used up to form products. But the reality is this isn't always the case. All right, reactions do not always go to completion, and this is what we call chemical equilibrium. All right, so chemical equilibrium is defined as the rate of the forward reaction and the reverse reaction are occurring equally. Okay, so the forward reaction and the reverse reaction are occurring at the same rate. Just because the forward and the reverse are occurring at the same rate does not mean concentrations are the same. It is the rate. The speed at which products are made equals the speed at which reactants are made. The concentration of the reactants and the concentration of products are not necessarily the same. Okay. If we were to look at the concentration of reactants and products, we would call that the equilibrium position. And the equilibrium position is used to determine if the reactants or the products are favored in a reaction. Okay, so let's take a look at this and see if we can't dive into this into a little bit more detail. First of all, let's go back to our chemical equilibrium definition where we said the forward rate and the reverse rate are occurring, or I'm sorry, the forward reaction and reverse reaction are occurring at the same rate. So if we were to look at an equation, nitrogen gas plus hydrogen gas forms ammonia gas. The forward reaction is going from reactants to products. The reverse reaction is going from products to reactants. So we have this double arrow. Our forward makes products. These products make reactants. That is the reverse. So when this equation is in equilibrium, the rate at which products are made equals the rate at which those products are then turned back into reactants. So we have a process where we are making products and reactants simultaneously, and we are going back and forth, back and forth. All right. Now we can calculate our equilibrium constant, and we can determine and use this to determine whether reactants or products are favored. All right, look at that equilibrium position to determine, and we call this the equilibrium constant. And this is going to be used to determine whether we favor reactants or products. Now your equilibrium constant, you see KEQ. KEQ is kind of a standard. We're talking about equilibrium. All right. We also write it as Kc, where C is concentration. K is our equilibrium. And now this is a big K, not to be confused with a little k from kinetics when we get to the AP portion. All right, so our equilibrium is a big K, and you will either see it EQ, and this is kind of all-encompassing. We have lots of different equilibriums. We have the Ka, which is the equilibrium of an acid. We have the Kb, which is the equilibrium of a base. We can look at Ksp in terms of solubility product constants. We can do Kc in terms of concentration. So we're going to really just stick with concentration at this point, and we're going to explore the different types of equilibrium constants when we get to the AP. All right. So our equilibrium constant, if we're looking in terms of concentration Kc, that is the ratio of product concentration to reactant concentration. And our formula to calculate our equilibrium is going to be the concentration of product raised to its mole over the concentration of reactant raised to its mole. And when we do concentrations and we look at equilibrium, we can only use gas and aqueous. Now, let's think about this in terms of some logical thought. If my numerator is larger than my denominator, I have more product. If I have more product, products would be favored, okay? A large number divided by a smaller number would give me a KEQ or a KC of something larger than 1, and this is products are favored. Now, if my reactant is larger than my product, a small number divided by a large number gives me a final K value that is less than 1, but I have more reactants, which is what gave me less than 1, so my reactants are favored. So let's go back to the original equation that I wrote to show us what a forward and a reverse reaction look like. And we're going to use this same equation to calculate concentration. All right, so let's write our equilibrium expression. Our KEQ, EQ for equilibrium expression, is going to be the concentration of products, which are NH3, raised to their mole. There are 2 moles of NH3. Over the concentration of reactants, I have 2 reactants. My first reaction or reactant is nitrogen. Raised to the mole, there is 1 mole times the concentration of hydrogen raised to its mole. So that is my equilibrium expression. Now, let's do a word problem. All right? At equilibrium, a 2-liter flask contains 0.15 moles of hydrogen, 0.25 moles of nitrogen and 0.1 mole of ammonia. Calculate KEQ. So, this is concentration, all right? Calculate KEQ, and we're doing it in terms of concentration. So why don't we could say KC if we wanted to. So the state uses EQ, so that's why we're using EQ here so that you can be prepared for your state exam. When we get to the AP portion, we're just going to make it say KC because we start distinguishing between the different equilibriums at that time. All right, so calculate this. Concentration is molarity. Molarity is moles divided by liters. So step one, I have to find the molarity of hydrogen, the molarity of nitrogen, and the molarity of ammonia. So I have 0.015 moles of hydrogen. The volume is 2 liters, which gives me a molarity of 0.075. I have 0.25 moles of nitrogen. Again, a volume of 2 liters. So that is 0.125 molar. And then ammonia is 0.1 moles. And the same volume, 2 liters. So that is 0.05 molar. So be careful, concentration is in molarity, so you must always solve using molarity. So if you're not provided molarity, you have to find molarity. So now we're going to plug these values into our equilibrium expression, where NH3 is 0.05, and it is squared. Notice I'm using brackets, not parentheses. Remember, concentration is brackets. N2, nitrogen is 0.125. Now, you don't have to write the 1 because anything is understood to be 1. So you don't really need that 1. So we'll just take that out. I added it in so you could see. But remember, if there's no 1 or no number, it's understood to be 1. All right. And hydrogen is 0.075. And that is cubed. So when I plug this into my calculator, I get 47. 47 is larger than 1. So my K is larger than 1. And since my K is larger than 1, that means my top number, which were the products, is larger than my bottom number. So products are favored.